In this video, we're going to discuss the enthalpy of reaction. So what do we mean by that? Well, if you have a reaction, say methane gas plus 2O2 gas going to CO2 gas plus 2H2O liquid. This is combustion of methane. When you burn methane on a stove, it gives off heat and heats up whatever you have on your stove. We use this to generate heat. Question is, how much? A set amount of methane will generate a set amount of heat energy. The enthalpy, written as the delta H of reaction, is minus 890 kilojoules. What this tells us is that there's a heat change, an enthalpy change, for this reaction. There's some work done that we don't follow, but the thermal energy released, minus 890 kilojoules. Well, we give away heat to the rest of the universe. So while you hold your hand above a stove and it feels warm, you're thinking, oh, there's heat here. The molecules no longer have that energy. It was trapped as potential and has been lost. The delta H reaction is talking about the molecules. The molecules had more potential before the reaction, they have less afterwards. So it is a negative value. But what that more or less suggests to us is that heat is a product. It's no longer in the molecules, it's been released. Now, we don't usually put this in a balanced reaction because balanced reactions are about the molecules. You have to have the same number on both sides of every atom in those molecules, and so we can balance the reaction based on the atoms, but you can't really see potential energy trapped in a bond from a molecular formula. And so we don't include heat in the balanced reaction directly. There's no reason we can't act like it is. If you want to do a calculation, and you were going moles of one chemical to moles of another, you could use a balanced reaction to go between them. You can also do this for the enthalpy. Let's do an example. If 10 grams of CH4 is burned, find H2O produced. So normally we would say, well, 10 grams of my methane, and it is 16.015 grams of methane in every 1 mole of methane. And according to balanced reaction, it is 1 mole of methane for every 2 mole of water. And we'll find that 1.249 mole of water ought to be produced. Well, we can simultaneously find the energy for this amount of methane, for 10 grams of methane reacting. Well, I know there's 16.01 grams of methane for every 1 mole of methane. And the balanced reaction tells me that for every 1 mole of methane, there is 890 kilojoules of energy involved, for what we can calculate to be 556 kilojoules. If an entire mole of methane had burnt with oxygen, the rearrangement of all of those atoms would have yielded 890 kilojoules of energy. We had less than a mole of methane rearranging with oxygen, so we have less than that energy. But 10 grams versus 16, about a third. 556 versus 900, about a third. You can actually directly calculate the amount of heat energy a reaction will give off by knowing the delta H of the reaction. Enthalpies of reactions are extremely useful for being able to calculate out what amount of energy is going to be released or consumed when a reaction occurs. We can do reactions like CO2 plus water goes to sugar, C6H12O6 solid plus dioxygen gas. And it is a 6 to 6 to 1 1:6 ratio. This is photosynthesis. Photosynthesis has a delta H of reaction equal to 2,840 kilojoules. This is positive. The atoms are gaining energy as this reaction occurs. Well, if we think about what the point of photosynthesis is, it harvests light. Plants sit out all day, absorbing sunlight, trapping that energy in order to build sugars. And so our delta H is positive in this case. All that really means is that it goes in. So if you're trying to treat it like it's part of a balanced reaction, it would be 2,840 kilojoules as a reactant. Nonetheless, we can treat it just as before, like it's part of the balanced reaction. If 93 grams of sugar are produced, we can find energy required. The same way we could find CO2 required, or we could find dioxygen produced. We start with the mass of our chemical. I'll just call it sugar for short. It is 180 grams of sugar in 1 mole of sugar. So we have about half a mole worth of sugar, just slightly over, 0.5167 mole. And we can convert that. There's 1 mole of sugar for every 2,840 kilojoules. 1,467 kilojoules. So to make 93 grams of sugar, the amount of energy required to produce it in the form of enthalpy is 1,467 kilojoules. So our enthalpy of reaction can be used to calculate out either the amount of energy produced in the process of making some amount of chemical, or if you know the energy, the amount of a reaction that must have occurred. It is just part of the balanced reaction for these calculations, and so if you know any part of a balanced reaction, you can solve any of the other parts. So this lets us relate energy directly to the amounts of reactants and products being produced or consumed.